I want to talk now about probability density functions. And I'm going to do an example in a minute, so let's get through these terms and they won't make sense right away. You have to play with probability for a while before it makes sense. Let's say there's a thing called a probability density function. It's always positive because probabilities are always positive. We're not going to have a negative 3% chance of snow tomorrow. Okay, you can have a 0%, but not negative. We're going to require that the total probability of all possible outcomes is 100%, right? Maybe there's a 30% chance it rains and a 70% chance it doesn't rain. They add up to 100%, which is 1. Said another way, the integral of your probability density function, and assume x is the variable, dx, is 1. That's a fancy way of saying total area under curve is 1. Making sure that shows up. I think I'm gonna have to get a new blue marker pretty soon. It's getting pretty bad. So the total area under the curve is 1. In general, the probability of x falling between two different values, say a and b, is the area under that portion of the curve. All right, that's what this is saying. And if your interval is small enough, like let's say you take just a tiny little slice right here, that area is approximately a rectangle. Okay, and so let's say, let me get this down here so I can show this. The width of this interval would be dx, and maybe it's centered on x0. If that is the case, the probability of the event occurring between x0 and x0 plus dx is approximately equal to this, right? If you slice this interval up small enough, you could just do the area of the rectangle. All right. So now in practice, what might this mean? Eventually, we're going to get to this. This could be the probability of having a certain speed. A molecule could have a certain speed, and that's what we're going to do first. Or later on, it might be the probability of an electron being located somewhere. So for example, this one actually is pretty nice for that. You could imagine this might be the probable locations of an electron in a molecule, and right, it could be at various locations. This might be near one nucleus, this might be near another nucleus, and so it's most likely to be hanging out in those spots. Wherever the curve is tallest, you're most likely to be found. Now, let me give you an example with some numbers worked out here. Let's go to the other board. And this is on page 83 in the workbook. It's related to, I'm going to try and explain how you could actually, you've already done this stuff, but maybe it didn't seem like it. So imagine you have a 2-meter long rod. That's what this is. Does that fit on the screen? Just barely. And then what you could do is you could change the density by overwrapping it a little bit. And then what you might do is as you get towards one end, you might start wrapping it more frequently. And then you keep wrapping, and then eventually some regions of this rod will have more wrapping on it than others. Oh my gosh, this is getting kind of crazy here. And then down here, maybe you're wrapping it really furiously. So in some sense, you could imagine the mass of the rod could be affected as you move left and right along the x direction. Kind of a quirky visual aid there, but it was laying around in the room, I went with it. Let's assume for right now, the linear mass density of this 2-meter long rod is basically 3x. Now if you check the units of lambda are kilograms per meter. So in order for this to work out, we need kilograms per meter squared times meters, which gives us kilograms per meter. If I plot this function, 3x looks like this. I can get this mass, the highest mass, right? That's just 3 times the final position, 2. So that's how I got these numbers. All right. Now, in this case, I'm going to very quickly figure out the total mass. The total mass is equal to the integral of dm. Well, dm is lambda dx, where lambda is not wavelength anymore. Lambda is the linear mass density. And so when you do this integral, what do you get? I think you get 3x, you get what is that, alpha x squared over 2 evaluated at 0 and 2. And when you plug that all in, you should get the total mass is 6. So this 6 comes from the integral. This 6 came from just plugging in the values. They aren't necessarily the same. It's kind of a coincidence in this case. If I'd used 3 meters, we wouldn't expect these things to match up. Now what I'm going to do is I'm going to do a process called normalization. I'm going to get a new linear mass density, but it's a linear mass density per unit mass. I'm going to divide through by that. And when I divide by mass total, the 3 in there basically becomes a 0.5 because mass total was 6. So notice what this function looks like. We have the linear mass density per unit mass. This is the probability distribution. Notice the units make sense. Probabilities have no units. Well, what do you get when you do an area of on this chart? You get height times width. Well, the units will drop out. That's what happens in a probability distribution. The area has no units because the area is a probability. That's cool, all right? If I wanted to find what fraction of the mass is between these two spots, I could look at these two spots right here, and I could get that area. And I believe I did the math on this already. So this is 31.25%. Or maybe if you're tired, right, you end up getting this decimal number, which is 31.25%. So we see that 31% of the mass is in this region. While this isn't exactly a probability distribution, it has a lot of similarities, right? We're not talking about the probability of an outcome here. I guess you could say you expect to find 31% of the mass there if you looked for it. But in this case, that's trying to show you how you could, basically you've already done probability distributions. So let's go back and look at the first board, see if there's anything else to say. Come on. All right. The units, we saw that the units were kind of a big thing. It's going to be 1 over meters here. So you have to be a little bit careful. P of x is the probability density function, but when you're plotting it, P is 1 over meters because these are the units in this plot. We've seen these different results. And so hopefully that gives you kind of a very quick crash course on probability density functions. We use this for the Maxwell-Boltzmann speed distribution, how fast different molecules are going in air, and also for quantum mechanics at the end of the semester. Schrodinger equation, all that.